Good. Welcome, everyone. We stopped last time with entropy, where we showed how we can use the concept of Huffman encoding. So we tried to encode a sequence of letters by a minimum number of bits to quantify sort of the uncertainty in an outcome of a random experiment. And we said we could consider the outcome of a horse race and then try to write down all the outcomes of a certain horse race, and then simply try to quantify the randomness, meaning how predictable a certain event is by quantifying how many bits we need to encode this. So the high-level idea is that with if it's as low randomness, meaning it's predictable in the sense that there's like certain events that occur more often than others, then you need fewer bits to encode such a series of outcomes. Okay, and are there any questions concerning Huffman encodings or the application in entropy? Otherwise, I will start a new subtopic, still in the area of greedy algorithms. No question. Good. So I'm gonna talk about a very beautiful combinatorial structure that is called Matroid, and Matroids describe a class of problems, again, for which greedy algorithms give optimal solutions. So we had sort of the general criteria formulated earlier in the very beginning of this chapter, where we said in order for a greedy algorithm to give you an optimal solution, it has to satisfy these three properties of being iterative, that you choose a certain element in each step, that you have this greedy choice property, such that every time you choose something, this choice is part of some optimal solution, and that you can sort of assemble all your choices together to form an optimal solution based on this optimal substructure problem. And in this case, in this Matroids, they sort of define a structure for which we know that greedy will always give you an optimal solution, and we will start with a formal definition of these Matroids. They won't cover all the cases for which greedy is optimal. Huffman encoding is a counterexample. This cannot be captured in this framework, but they do capture a lot of practically important problems for which greedy gives an optimal solution. So let's start with Matroids. So I'll first give you a formal definition. A Matroid has two components. It's an unordered pair of two components. We denote by S and by I, capital I. Such that S and T satisfy, S and I satisfy the following properties. First, S has to be a finite set. And more interestingly, I will be a subset of the power set of S, so it will be a set of subsets of S. So we write this as I subsets of P of S. So this is the P of S is the notation I'm using for power sets, or that is generally used to indicate power sets, which describes all subsets of a given set, and I will be a subset of that. So it's a set of subsets. And in this context, we call these subsets independent sets. And these independent sets have to satisfy two properties. The first one is called hereditary, meaning that if one set is independent, meaning it's contained in I, then every subset of that set also has to be contained in I. So more formally, if I have a set B that is in this set I, and I have another set A that is a subset of B, then A must also be in I. Then it's A is also an independent set. So all subsets of independent sets are independent. This is what this says essentially. And the third property and last property that we need to define matroids is the so-called exchange property, which simply states that if you have two independent sets of different sizes, there must always be an element in the larger size that is not contained in the smaller size that you can add to the smaller size and still obtain a set that is independent. Okay, let me write this down. This is called the exchange property. Which says that for two different sets A and B that are both independent, so they are in I, for which the size of A is smaller than the size of B. So if I have two such independent sets in I, then there must exist an element X in B minus A, such that I can add this element to A and obtain something, a new set that is also contained in I. So this is the formal definition of a matroid, and it might get more clear if we start with an example. And the example I want to give is a so-called graphic matroid. And in the graphic matroid, so a graphic matroid is based on an undirected graph. So let's say you're given an undirected graph. G, node set V and edge sets A. Then the so-called graphic matroid MG is composed of a finite set SG and a set of subsets of SIG. Which will be defined as follows. So SG, the elements in our graphic matroid, has a question. Yeah, I thought this was not very optimal here. So this doesn't exist. So in the graphic matroid, S will simply contain all the edges of your graph. So SG will be equal to E, set of edges. And A, meaning a subset of these edges, this is a subset of E, will be in our set I, if and only if A is acyclic. So what is GA? Would you recognize that? If I say that starts including in S all edges in our graph. And I consider any subset of these edges that is acyclic. Then how do you call this graph that contains the edges in A? You have seen this before. This one here, what is GA? So GA contains the same node set as our original graph, and it contains as edges all elements in A, and A contains edges that are forming no cycles. Yeah. A spanning tree is one possibility. So A could be a spanning tree, but more generally, so it doesn't have to span all the nodes really, right? We didn't have any requirements in that. So any subset of edges that doesn't contain any cycle, you could take a single edge, and a single edge would be also a feasible set A. So what are these structures then called in a graph? It is acyclic, but the name of that structure, maybe you haven't heard this, but it's a forest. Have you heard of forests? Just like individual components that are acyclic, but not necessarily are connected. So you have individual connected components that are acyclic. So for any set A that is in our graphic matroid, if you use this set of edges, you get a forest in the graphic matroid. This is called, meaning that GA is a forest. As an example, let's say we have graph G with the following nodes. You have nodes 1, 2, 3, 4, 5. It's this set of edges. So this is our input graph, and based on this undirected graph, we define a graphic matroid, which contains in S S will be simply the set of edges. So it contains edge 1, 2, for example. It contains 2, 3. Contains 1, 3. So on. So this is how our set S looks like. It contains all the edges of this graph. And our set I, G, will be all forests of our undirected graph G, which so IJ is a set of all forests of G. Which, for example, contains the set that contains a single edge, for example, 1, 2. So 1, 2 forms one possible forest. 1, 2, and 1, 3 together from another forest, and so on. In this structure, we can verify to be a matroid. So what would we have to do to show that this graphic matroid is indeed matroid? I mean, for one, I call it matroid, so it's a good indication it's a matroid. So I just told you basically how I'm going to building sort of these subsets. I just take always a forest, and this will be my elements in set I. And so this defines S. The set of elements in our Matroid are simply all edges, and we have set I, which contains simply all forests. So now how to show now that this structure is in fact a Matroid? What will we have to do? Well, we have to show two properties, really. I mean, three, yeah. Yeah, which is the case because it's simply a set of edges in a graph. Okay, S is finite. The second thing we would have to show is this hereditary property. Is that given? No, I mean, you know the answer, but why is it true? So just as a reminder, hereditary simply means that if you consider a subset of the elements of an independent set, the resulting set is again independent. And we said a set is independent whenever the set of edges form a forest. So that simply means when you start from a forest, this would be our independent set, and you take a subset of the elements, in our case edges. If you take a subset of the edges of a forest, then the resulting set of edges again must be a forest, meaning you cannot by removing edges, you cannot introduce any cycles, right? And that's why any subset of a forest is again a forest, and therefore is an independent set really in your Matroid. And the last property you would have to show is this exchange property. If you have two forests of different sizes, we can always find an edge in the larger forest and add it to the smaller forest, and again obtain a forest. And that's not immediately visible, but it can be shown with a little bit more effort, and which is done in the book. But we're not gonna do this here. But in any case, you can verify that this structure here, this graphic Matroid, is indeed a Matroid according to the definition of Matroids. So let's see how we can establish relationships between different sets in this independent set. The first relationship is a so-called extension. If I consider some element in I, some independent set, then we say that an element X in S is an extension of I whenever, yeah. One more second. So you said this one, this is a forest. 2, 3 is a forest. It's a single edge. Every single edge is a forest. And what is your claim? Right, this one. No, you're adding here, according to this definition, you're adding an element of the larger set to the smaller set. So this only says that there exists an edge among these two edges that you can add and get an independent set here. Basically, you can add, for example, 1, 2. Actually, you can do in both cases. 1, 2, and 2, 3 again will form an independent set. So for a given element in I, so a subset of our elements in S, we say that an element X is a so-called extension of A whenever we can add it to A and obtain another independent set. So for A in I, we say that X element S is an extension of A if we can add it. So if A union X is again in I. And then based on this definition, based on the definition of extensions, we can define so-called maximal sets. So a set A in I is maximal if, yeah, what? Any suggestion? When is A maximal, intuitively speaking? Just by the typical meaning of maximal. Sorry? There is no extension exactly. So there's no element that we can add and get another independent set. So this is what it means if A is maximal. There's no extension. And the nice property of all of these maximal sets is that they all have the same size in the Matroid. So there can't be different maximal sets that have different sizes. Theorem, which simply states that all maximal sets have the same size. Can anyone see why that must hold? So why do all maximal sets have the same size? Any idea what would happen if not? So if you had two maximal sets that's of different size, what could you do? Yeah. No, we're not. So it's maximum is different from maximal. It just means that you can't extend it. In principle, there could be two maximal sizes or maximal sets of different size. It just means that you can't extend them anymore. In Matroids, this can't happen. I mean, cannot happen. Any suggestion why not? Exactly. Yeah. So because of the exchange property, if one was larger than the other, you could take one element of the larger one, and I mean, there exists one element in the larger one that is not part of the smaller one that we could add and make the smaller one larger, which is a contradiction to the maximality of A. Yeah. So let's write down this one line proof. Let's suppose to the contrary that we have two sets A and B of different sizes. So let's say there exists some B in I such that B is strictly larger than our maximal set A. Then the exchange property says that there exists an element X in B minus A, such that we can add this element to A and still get an element in I. So A union X would be I, which is a contradiction to the maximality of A. What about the graphic Matroid? How do the maximal sets look like in graphic Matroids? So in graphic Matroids, we have this graph and all the elements are edges and the subsets are forests. So when is such a forest maximal? And how many elements does it contain? So if you had to return a forest that contains the maximum possible size of number of edges, what would you end up with? I think we had it before. No one? Yeah? A spanning tree, exactly. So the maximum size forest in this case is a spanning tree. But it cannot be, and they all have the same number of edges, namely number of nodes -1. And very often we're not interested in sort of an element that has the largest number of elements, but we're interested really in something that is composed of very valuable elements. So we usually have weights in certain problems, such as the minimum spanning tree problem. And therefore we define a weighted matroid simply as a matroid that has strictly positive weights on its elements in S. Here comes the definition. I think this is the time where I switch to the keyboard. A weighted matroid is a matroid M composed of finite set S and subsets I, along with strictly positive weights. Note by W that I assign a strictly positive number to every element S. And based on this definition, we extend this weighting scheme to the sets in I simply by summing up the weights of the edges contained in our set. So we extend to sets simply summing up the edge weights in A. And in a graphic matroid, it would simply mean that we have edges on the weights, and the weights of a subset of the edges, meaning of a forest, is simply the sum of the weights of the edges in this forest. So in the graphic matroid, W should simply give edge weights. And from many problems for which greedy gives an optimal solution, we can phrase this problem as finding a maximum weight independent set in a weighted matroid. And one prominent example is the minimum spanning tree problem. Here's an observation. So a minimum spanning tree can be cast as maximum independent set problem. By setting, so what's missing here? How do we phrase the minimum spanning tree problem now as a maximum independent set problem in a weighted Matroid? We already saw the graphic Matroid. We said that every element, every independent set forms a forest. Now we have assigned strictly positive weights on all the edges. So an independent set of maximum weights will always be a maximal set, one that we cannot extend with additional elements since they're all strictly positive. So the optimal solution in this among these maximum independent sets must be maximal. So there must be there must be spanning trees. So far so good. This is exactly what we want. We simply need to find a maximal independent set in a Matroid. But how do we map the weights between these two? So we're in the minimum spanning tree problem, we're trying to find a set of edges spanning all nodes of minimum weight. And here we're trying to find an independent set such that the sum of the edges in this independent set are actually maximized. How would you do that? How can you phrase the minimum spanning tree then as a problem of maximum independent sets in Matroids? Any suggestions? You had something similar in the homeworks, I believe. Homeworks or recitation, I'm not sure which one. So how do I make out of a minimum spanning tree problem a maximum independent set problem in Matroids? The structures are identical. I think you see this, right? So that the maximal independent sets in this graphic Matroids are spanning trees, but how do I find the one that has the minimum weight using the maximum weighting scheme in the graphic Matroids? Well, I just multiply these edges by -1, right? And then the maximum independent set will correspond to a minimum independent spanning tree. And since we require strictly positive weights, after multiplying these edges with -1, we have to shift them to make them all strictly positive. So we simply take the edge of maximum length and add a constant that is larger than that maximum value. And then we would simply solve the maximum independent set problem in the resulting weighted Matroid to get a minimum spanning tree in the original graph. So let me write it down and then maybe let's give you some time to think about it and to ask questions. Actually, I wrote it already. Forget it. Yeah. Setting here the weights are W. So the weight of an edge will simply be some constant C minus the original edge weights. Just call this original W of our edges. So these are original W are the weights in our undirected graph in which we want to find the minimum spanning tree. And C, as I said, is something that is larger than the maximum edge length in our graph. Then you can see that all these terms, all these weights of these edges will be strictly positive. So this is how we build our Matroid, and now we only have to solve sort of the maximum independent set problem in a graphic Matroid, and we obtain a minimum spanning tree. So let's see how we do this actually. If we have a Matroid, how do we find the maximum weight independent set in such a Matroid? We do this again with a greedy algorithm. And this is a greedy algorithm that will not only work for minimum spanning trees or graphic Matroids, but it will work for any Matroids, any weighted Matroid that you can come up with, including the graphic Matroids. So this greedy algorithm gets as input a Matroid M equal S and I, and it has weights on the elements in S, W. And it's very conservative. It starts with an empty set of elements. So we start by setting A be equal to the empty set. Then we take our elements in S and sort them in monotonically decreasing order by W. Take our elements and sort them. Decreasing order by W. Trying to maximize, and that's why we start with the heaviest edge. And then we simply iterate through all our elements in this sorted order for each S in S. I'll call this X. So for each X in S, we will simply check if we can add X to our current set A to obtain something that is independent. So if A union X is an I, so it's safe to add X to our current set A, then I'll do that. So A will be equal to A union X. Once I have tried all the elements in S, I can return this final set A. Intuitively, it makes total sense. We start from something that is empty. So we have no elements in our set A, which is independent by definition. We know that the empty set must be part of any Matroid. So we start from something independent. And then we iterate over all our elements in S and start from the heaviest one, try to add it to our current set A. If this gives something that is independent, we add it, and otherwise we don't. And then once we have seen all these elements, we just return A. Does this remind you? Yeah, there's a question. That is very problem specific. Here I'm being vague and I'm just, but it's a good point. And this is, yeah, it depends on the problem. We'll see an example in a minute. Does this algorithm remind you on something? An algorithm that you have seen before? You have seen many algorithms now, many greedy algorithms. Yeah, exactly. It's exactly the Kruskal algorithm, except that we sort it in decreasing order instead of increasing order. So trying to maximize, but otherwise it's the exact same idea. So we start from an empty set of edges. So A is equal to the empty sets, and then we iterate over all elements in a certain order, which is different here a bit. And then we try to add every element one after the other to our current set of edges. And whenever the resulting set either doesn't close a cycle or more generally gives an independent set, then you add it, and otherwise you just proceed. So it's the exact same algorithm. It's a special case of this algorithm, I should say. So Kruskal is sort of a special case of this algorithm when applied to the graph that corresponds to the graphic Matroids. Okay, but this is a more general greedy algorithm. This solves the maximization problem for any kind of Matroid, not only graphical Matroids. So how about the running time of this algorithm? Should be relatively straightforward. So let's denote n to be the number of elements in our set S. So in the graphic Matroid, this would be simply the number of edges. And then for sorting, we know by now we need time n log n. And let's say that checking if A union X is in I is order of some function f of n. And again, this f will depend on the exact problem that you're trying to solve and the structure of this Matroid. So if we generalize this and just say, well, this is some f of n, order f of n, then the total running time will be order of n log n plus n f of n. Okay, so this is our n log n for sorting, and then we have to iterate through all n elements and spend f of n for every check in these n iterations. And by induction, we know that this algorithm always gives us an independent set because we start from an independent set. The empty set is independent. And in each iteration, we check for independence and only add something if we get something independent. So at the end of this algorithm, we will get an independent set. But of course, it's not good enough. We want to actually not have only any independent set. We want to have the one with maximum weight. And how do we show that? Any suggestions what you would do if you had to show that this algorithm doesn't give you only an independent set, but it gives you one of maximal weight? Well, we're back to the original scheme. We have a greedy algorithm. You want to show that it's optimal. We have to show three properties. A, that it's sort of a sequence of choices, and that every choice is safe in the sense that it's part of an optimal solution, and that the whole thing exhibits optimal substructure. So this is something we don't do here, but it's done in the book. And this is the way to show that this greedy algorithm gives you an optimal solution for any Matroid. So this greedy algorithm exhibits all three properties, namely it's iterative, it's safe, and it has optimal substructure. So we know that it will return an optimal, and in our case, maximal set A. Any questions? If not, then I want to give you an example application of this, namely for the so-called task scheduling problem that we will phrase as a Matroid problem. Task scheduling as a Matroid problem. This is sort of one example application of this idea of finding maximum independent sets in Matroids. And in this setting, in the task scheduling problem, we are given a set of unit time tasks. So every task will take exactly 1 unit of time. And for every task, you have a certain deadline that you have to satisfy. So the task has to be finished by a certain time. And every task has also assigned a penalty, which you will have to pay once you schedule this task at a time after its deadline. So whenever this task is finished after its deadline, you will have to pay a certain penalty. And the goal is to come up with a schedule, meaning an ordering of these tasks. So which tasks are you going to schedule on a single processor, let's say, in what order, such that you pay the minimum possible penalty, such that the penalty for all tasks that are late, in the sense that they finish after the deadline, is minimized. So this sounds a bit dirty, this problem, lots of ingredients and constraints. Sounds at first glance difficult to solve, but in fact, this can be very nicely phrased as a Matroid problem with based on some additional insights on these optimal solutions. And this is what we're gonna do now. So here's the formal setting that I have just mentioned. So think of programs that you want to run on a single CPU. So CPU scheduling programs to run. And the setup is as follows. So we have a set of unit time tasks. So S is a set of tasks, A1 through AN. So we have N unit time tasks that you want to schedule. Then we have for every task a deadline, which we denote by D1 through Dn. So Di is the deadline for task I. These are, as I said, integer deadlines. By which these tasks must be completed. These deadlines are all integers between 1 and n. So a task cannot finish before time 1. And if it has a deadline after n, it's also trivial. We only have n tasks and units time tasks. So we assume that all the DIs are between 1 and n. And the last ingredient is that we have these penalties, Wi, going from 1 through n, W1 through n, Wn. And these are non-negative penalties that we have to pay if AI is not finished by its corresponding deadline, Di. These are non-negative penalties. Need to pay if AI, the corresponding task, is not finished by deadline Di. And otherwise, we don't have to pay any penalty. So if a task finished before its deadline, we're happy. And what we try to come up with is a so-called schedule. The schedule is simply a permutation of our tasks, an ordering of our tasks that specifies when we do which task. Schedule is a permutation of S. Specifies when to do these tasks. So this schedule simply gives us an order of these tasks, which says that the first task, according to this order would be processed between time 0 and time 1. The second task would then be processed from time 1 to time 2 and so on. And the goal will be to find such a schedule, an ordering of these tasks that minimizes the total penalty that we have to pay for the tasks that are late, meaning that finish after their deadline. Find schedule S. That minimizes the total penalty. Okay, is the setup clear to everyone? So what we're trying to solve? Okay, so then comes two insights in how these optimal schedules look like that will help us later actually to find such a schedule. So the first property of a schedule is what we call early first, which simply says that any schedule can be transformed into one where we have first all the so-called early tasks, meaning those that finish before the deadline, and then we have all late tasks that finish after the deadline. So we only have to think about schedules that have that specific shape. Okay, so we can transform any schedule into what's called early first. So here's an example, or more like an intuition why this is true. Let's say we have a schedule that looks like this, where we have some tasks, then we have task AI, then we have some additional task and task AJ, and then maybe more tasks after that. And let's say these two tasks sort of violate this property that we have first all the early tasks and then all the late tasks, meaning that AI, which comes before AJ, is actually late. Let's say that this one is late and this one is early. So again, late and early just with respect to their deadlines. Then what can we do to fix this? Any suggestion? Yeah. We swap them, and why does this work? So we can swap them. Exactly. So if it was late before and you move it, if it was early before and you move it earlier, so you swap AJ to the left, it will still be early. And if AI was late before and now you're moving it further to the right, so you schedule it later, it will still be late. So early will remain early and late will remain late. And therefore, the cost of the schedule will not change. And we can keep on doing this until we have sorted all tasks into early first and then followed by all the late tasks. So this will give us AJ followed by AI. And again, AJ would still be late. No, wait. True. So AJ was early and now we moved it to an earlier point. So AJ is still early. And AI was late and now we're scheduling it even later. So this will still be late. And therefore the total penalty won't change with this swap operation. So this early first structure is sort of the first part of this. The second part that we do to obtain a so-called canonical form is the following. So to obtain a canonical form of our schedule, we want to have all the early before the late using the previous property and the previous swapping idea. And then we want to have all early ones ordered by their deadlines. So early must come before late. And this we have already achieved with the previous operation. And the early ones are ordered with monotonically increasing deadlines. How do we achieve that? That ordering without changing the cost of our schedule. We'll do a similar swapping operation, but now in this case, we only consider two consecutive elements that violate this ordering according to deadlines. And then you will see if you have two tasks with deadlines that conflict with this ordering. Again, the one that was sort of to the right can be moved earlier without changing the fact that it's early, and the other one, so it's only really the one that you have to think about is the one that you will schedule later. So the risk is that this one might not be early anymore. But since it's moving only one position to the right, and the one that was previously to the right actually had a larger deadline, and it was still fine, then after moving this to the right, it will still be fine. So this is maybe easier if you, for yourself, make a little picture, but it's a very similar idea to the early first schedule. And with the swapping of consecutive elements that violate this property, you can get such an ordering of these early tasks. So this is how you get a canonical form. So again, a canonical form, in a canonical form, all the early tasks will come first, and then they're ordered by their deadlines, and then comes all the late tasks. And now, why does this help us? It helps us because now we know that if you want to search for an optimal schedule, we only have to find an optimal schedule that has this specific structure. And to find such a schedule that has this optimal or the specific structure, we only have to find really the set of tasks or the subset of tasks that you want to schedule early. Because once we have decided which tasks will be scheduled early, we know what to do. We will take all their earlies first, sort them by their deadline, and then let them follow by all the late tasks in this case. But the only thing we have to find is like a subset of the tasks that can all be scheduled early. And then the canonical form does the rest for us. We don't have to worry about this. Again, it's find this, and this is the part that we actually will define as a Matroid. So far, this is nothing to do with Matroids. And now, based on this observation of canonical forms that are sort of determined once we are set on a subset of the tasks that are early, that this sub problem of finding this early subset is actually what we will solve using a Matroid structure. So based on this, a set A of tasks is independent, meaning part of a Matroid if there exists a way to schedule them so that no task is late. So set A tasks is independent if there exists a way to schedule these tasks so that no task is late. Based on this definition, we define our set I in our Matroid simply to be all sets of independent sets of tasks. So now the original problem was to find a way to schedule all tasks to pay the minimum possible penalty. And now looking at this Matroid, what we really want to do is to come up with a set of early tasks for which we maximize the penalty. And this maybe takes you a minute to think about that, to see that this is really the same thing. So if you have a set of schedules, a set of tasks, and instead of minimizing the penalty of the late tasks, we're trying to minimize the penalty of all the remaining tasks, meaning the early tasks. Does everyone see that? So because these two sets really partition the entire set of tasks. And in the original formulation, I would have to pay a penalty whenever a task is late. And this is what I tried to minimize. So now I'm trying to essentially subtract as much penalty as possible, meaning that I try to schedule as many tasks, not as many tasks, but the total penalty of all early tasks should be maximized. This is basically what I'm trying to subtract from the penalty I have to pay in the end. Because everything that I cannot schedule early will in the end be a real penalty for me. And this is what we're trying to do now in this Matroid. And so if you find an optimal solution in this Matroid that we have just defined based on the set I that contains all independent sets, then we are done. We have found a schedule that minimizes the entire penalty, also based on the canonical scheme. So the only thing left now is really to show that what we came up with now, the set of I, the set I of sets of independent tasks, that this forms a Matroid. Okay. And to show that this set I of independent tasks is a Matroid, we have to first show that I has this hereditary property. And anyone sees why that's the case? Or is it the case? So this set I that I defined here, which contains all independent sets of tasks, where a set of tasks is independent if you can schedule them without being late. Why does this have this hereditary property? So again, hereditary means that you take a subset of your independent set of tasks and again get an independent set of tasks. So why is that the case? Well, if I have an independent set of tasks, I can schedule them by definition such that none of them is late. And now, if I consider a subset of those, I just remove some of these tasks, and then clearly the remaining tasks will still be scheduled without any delays, because everything actually will be moving to the left or stay the same. So we schedule it either earlier or at the same point as before, and therefore, if it was early before, it will still be early after removing some of these tasks. And that's why every subset of an independent set of tasks is still independent. So this is relatively clear. Or is it? Is it clear? So this set I is hereditary. And the second thing we have to show is that it has this exchange property. So to show this, let's say that we have two independent sets of tasks, B and A, and let's say that B is strictly larger than A. So what this exchange property tells us is that we have to find a task in B that is not an A, that we can add to A and obtain another independent set of tasks. So both B and A are in I. How do we do that? Well, we simply look at the time when the last task in A finishes, and then we take the first task in B that finishes after that time, which must exist because B is larger than A, and this one we can add simply at the end of the schedule in A and still get an independent set of tasks where nothing is late. So in this case, let K be the time and the last task in A finishes. And let X be the first element in B that finishes after K. So this again exists because B is larger than A. And then it's clear that I can easily add that element X after K, and it will still be an early task. So we won't miss any deadlines. And therefore, A union X will still be independent. And this shows both properties, the hereditary property and the exchange property. And therefore, we know that this structure of tasks S and independent sets of tasks in I is a Matroid. And because it is a Matroid, we can use the greedy algorithm that we just introduced to solve it, meaning to find a maximum independent set of tasks, meaning a set of early tasks with maximal penalty, which means that the remaining tasks, the late ones, will have a minimum penalty. So there exists greedy algorithm to solve this one. Does everyone see that? So once we find the maximum independent set of tasks, that we're done. Once we have this, we know that the rest is sort of minimized. The penalty of all tasks that remain, the late ones, will be minimized. And then using the canonical form, we can sort of easily write down the schedule by first starting with all the early tasks, sorting them by deadline, and then having all the remaining late tasks in the end. And this gives us our final schedule. And so using this greedy algorithm, we can do this in time n log n plus n times f of n. And in this particular case, I'm not going to show how you can check if a set of tasks is independent, meaning there exists a schedule in which none of these tasks is late. You can do this in linear time, O of n. So checking if I union X is independent, meaning in I takes order of n. And so the total running time order of n squared. Okay, any questions? If not, then I'll stop here and not start sort of a new topic, and then we continue with Horn formulas on Thursday. Yeah.
I ask like where I can find those things.
Which one?
About
So Matroid is all in the common book.
Oh, not in this.
It's not in. Let me just turn this off. That's too loud.